Good morning, class. The session is being recorded. We are looking at 4.2, how derivatives affect the shape of a graph. We looked at max and minimum values, differentiation formulas, the synopsis of what we covered, absolute, the same as global extrema, local, the same as relative extrema, finding a critical point, f prime set it equal to 0 where it doesn't exist, and the closed interval theorem. The summary of the section: a function is increasing where f prime is positive, decreasing when it's negative. A critical point and definition was given previously. A relative max or relative mean is a critical point at the top or bottom of an interval of a graph. A function is concave up where f double prime is positive, and it's concave down where f double prime is negative. Concave up, the graph is completely above the tangent line, and concave down is completely below its tangent lines. And of course, the point where the change happens, the change of concavity, is known as IP, the inflection point. To graph a function, we use previous course, Precalculus. Okay, that means finding intercepts, behavior near an x-intercept, the end behavior, and now we add calculus by finding relative extrema, inflection points. We put the whole thing together and we graph it. Again, a function is increasing where f prime is positive and decreasing where f prime is negative. When the change occurs from increasing to decreasing, it's a location of a local max. When the change occurs from decreasing to increasing, that's a location of a local mean. And a sine graph shows that. This is known as the first derivative test. When f double prime is positive, the graph is concave up. When it's negative, it's concave down. And the point where the change occurs is known as the IP, or inflection point. And again, sine graph is the one that will give us the details. We looked at this graph. This was a polynomial of degree 3. I mentioned the information about odd and even. When the leading term has a degree which is odd versus leading term which is a degree which is even, how we graph it, the end behavior. Okay. Also the end behavior, the behavior near an x-intercept. Also the intercepts, all of them put together, we graphed it already. We added the information from calculus, and there you have it. We want to look at more graphs and more examples. So we did this. Here's the function we want to look at. And to do that, I'm going to look at it from the point of view of a precalculus again. And we'll see how it's done using precalculus. If f of x is 1/2 x to the power of 4 minus x squared, what do we need to know? Notice a sub n is a 1/2 x to the power of 4. So the degree is even. And this number is positive. So having said that, that means the end behavior is like y equals x squared. So as far as the end behavior, we deal with the first and the second quadrant. We also add the intercepts, and pretty much we have the graph. Remember, you set y equal to 0 or f of x equal to 0 to find the x-intercept. So when we do that, if I factor out 1/2, let me use a different color. X squared, I get x squared minus 2. If I set this one to 0, x becomes 0. If I set this one equal to 0, x is plus minus square root of 2, which means I have negative square root of 2 comma 0, positive square root of 2 comma 0, also 0, 0. There are 3 intercepts. So let's plot those. I have 0, 0. Now, square root of 2 is roughly 1.41. This is not going to be to scale. So this is 1 point. This is 1. This is another one. Okay. And notice that this one, because of the 2, has a multiplicity 2, which is even, looking like that. So if I'm graphing, by the way, I do have all the information I need as far as the intercepts, because 0, 0 is both x as well as y intercept. So when you start from here, you bring it down, you hit your x intercept and it goes down, but it has to come back up at some point and hits the other x intercept, but it bounces back. That's why I put the arrow. Okay. Then has to come back up. And the graph looks something like that. What also helps is that if you notice that this function is an even function, because f of minus x, you can show that, is equal to f of x, that will help graphing, because the right half and the left half must be identical, because the even functions are symmetric. WRT with respect to the y-axis. So this is a rough sketch, and the difference is we don't know when the turn occurs, because we need a calculus to do that, and that's exactly what we are going to do now. So finding extrema and the intercepts were discussed. So I need f prime of x. When you take a derivative, 1/2 times 4 makes it 2, x cubed minus 2x. You set this equal to 0 by factoring the 2x out. So you got to take the 2x out. X squared minus 1 factors out to x plus 1, x minus 1, resulting in 3 answers. This one gives us 0, this one gives us -1, this one gives us +1. So we have 3 critical points, class, which means we have a number line. The 3 critical points, -1, 0, 1, we put them in order at the bottom. F prime goes at top. At -1, f prime is 0. At 0 is 0. At 1 is 0. And I hope you realize when you look at this, each and every one of them has a degree odd, has a degree 1 more specifically, x to the power of 1, x plus 1 to the power of 1, x minus 1 to the power of 1. Which simply put means if you evaluate any of them, if you figure out the sign here, the rest of them really, they alternate, okay? The rest of them alternate, and that's important to know. So what we are going to do, I'm going to look at one of them, for example. Right here, if I pick up a TP, short for test point, to the left of -1, let's say -2. And what we do, we put the -2 into f prime of x, either this format or the factored format, makes no difference. Factored format may make it a tad easier. This is negative. If you plug in negative 2, x becomes negative 2, right? Negative 2 plus 1 negative, negative 2 minus 1 negative. So negative times negative is negative. So if this is negative, you can pick up more test points, or as I mentioned, just alternate. This is negative, then this is positive, negative, positive. I'm going to show it with the arrows, and the reason is very simple. Negative arrow down, that means decreasing. Positive arrow up, that means increasing, decreasing, increasing. So arrow down, decreasing, arrow up, increasing. From decreasing to increasing, this is a location of a minimum. So the minimum occurs at x equals -1. The maximum occurs at x equals 0. And another minimum occurs at x equals 1. Now, what is the pair? Well, you have to put them back into the original function. If you put -1 or +1, they give you the same result, okay? 0 clearly gives you 0. So let's do the evaluation, okay? What happens if we plug in 1 or -1? Let's actually do that. So 1/2 plus minus 1 to the power of 4. We'll discuss this in a moment. Minus plus minus 1/2 to the power of 2. Either one of them to the power of even becomes 1. Therefore, we are looking at 1/2 times 1 minus 1/2. Okay, minus 1, which really means you're looking at 1/2 minus 1, which is negative 1/2. Therefore, local mean is equal to negative 1/2 at x equals 1, at x equals -1, and these are the two pairs. We plug in 0, it gives us 0. So local max occurs at 0, and local max is equal to 0. The function is increasing with the arrow up. So from -1 to 0, union 1 to infinity. The function is decreasing, arrow down, or negative, from -infinity to -1, union 0 to 1. Again, look at the domain. The bottom is the domain in essence, the top is the range, f prime of x, okay, for f prime. Therefore, increasing, decreasing. So what did we find? Intervals of increasing, decreasing, local extrema. The next one is to find inflection point or points. That means we are going to find f double prime. So here's the information from the previous page. Here's the function. Here's the intercepts. Here's f prime. Okay, so let's differentiate it again. 6x squared minus 2. Because we want to set this equal to 0, we're going to factor out, and we get those two answers. I want to make sure everybody understands why this is the case. We take the 2 out. And then if you set this one equal to 0, (3x squared is 1, x squared is 1/3, and x becomes plus minus 1 over square root of 3. Let's do the sine graph on that. Even though we haven't changed this to a decimal representation to understand what this number is, for sure one is negative, one is positive, okay? So if I want a sine graph, the easiest way would be to notice that, by the way, this gives you 2 answers. Therefore, in essence, if you were to factor it, you get 2 factors, and each one has exponent 1, so the things alternate up here. The easiest one would be the number in between, which is 0. So if I pick a test point, in between, I'm going to call it TP of 0. That would make life easy. How do we do that? We put the test point into f double prime, either this one or this one, it doesn't matter. I hope either way, when you put 0, I hope you realize you get negative. So over here is negative, class. So what about the other ones? They alternate. So this is positive. This is negative. This is positive. Okay. So what does it mean? It's positive here, concave up from negative infinity to negative 1 over square root of 3. Union, this is positive from 1 over square root of 3 to infinity. In between, we have a negative sign, so the function is concave down. Since the change occurs, this is the location of a low in IP or inflection point. This is the location of an IP or inflection point. Both cases, we have to plug in and find the pair. So concave down in between class, concave up beyond the two numbers. Again, we need the decimal representation for the sake of graphing and pinpointing the pairs. Now, if we plug in, notice what happens. I want to quickly show you. Because the exponents are both even, positive or negative makes no difference. So let's plug in plus minus 1 over square root of 3. We are just plugging in 1/2 plus minus 1 over square root of 3 to the power of 4 minus plus minus 1 over square root of 3 to the power of 2. So let's, first I want to look at this one. I hope you realize if you raise this to the power of 2, you get 1/3. So this is 1/3. So when you raise it to the power of 4, that means 1/3 squared, which is 1 over 9. This is elementary algebra. I hope everybody is following that. So a quick recap, plug in. When you raise it to the power of 2, you get 1/3. When you raise it to the power of 4, you get 1/3 squared, which is 1 over 9. The product of these two is 1 over 18. Therefore, 18 is the common denominator. So minus 1/3 becomes minus 6 over 18, so it's minus 5 over 18. Therefore, we are going to write IPs at these pairs, and we write it plus minus 1 over square root of 3 minus 5 over 18, both numbers. For the sake of graph, we change them to decimals. In fact, you can say it's roughly about 0.6 or plus minus 0.6. And you can even say this one is minus, I don't know, 0.3 roughly, for the sake of graph. Let's write the summary, everybody. Okay, so the x-intercepts at plus minus square root of 2, and remember, square root of 2 is about 1.410. Maximum occurs at 0, 0. IP location as such, and the minimum occurs at plus minus 1, negative 1/2. So let's plot the pairs, okay? This is negative 1.410. Now we're going to put 1.410 here. This is 0, 0. And remember, since this is a max, in essence, you have an arrow that means it can't cross that. We put the IP address using this, 0.6, negative 0.6, roughly negative 0.3. And then positive 0.6, negative 0.3. Okay, look at those IPs. Now minimum, minus 1, negative 1/2, plus 1, negative 1/2. So those are the pairs. And remember the end behavior. So the end behavior means, okay, we're going to come down this way. Okay, and remember, this is the minimum class. So it can't cross that. This is a minimum, can't cross that. This is a maximum, can't cross that. So it hits the first x-intercept, it crosses it, and then it has to, when it gets to the minimum, bounces back up, goes through that, hits the maximum, local maximum, bounces back down, goes through the next IP, hits the minimum, bounces back up, and goes up, looking like that. Again, by no means this is to scale, but it pretty much gives you the details. As you can see, intervals of increasing, intervals of decreasing, local extrema, IP, inflection points, all of them are there, okay? All of them are there. So you see from here to here, concave down, up, concave up, concave up. So everything that we've come up with works out here. Here's the next example. The number of bacteria in millions is given. We want to find the initial value. Initial population means plug in t equals 0. So if you plug in t equals 0, this goes to 0, this goes to 0, the answer is 100. And why is it in millions? Because it says so here. So that's the initial population plug-in. At what time before 10 hours will the population be maximized? Let's write a couple of things here. So this one is 10t minus 2t cubed. If we put this in descending order and combine these two, we get the following. N of t is minus 2t cubed plus 24t plus 100. We go from 0 to 10. Notice 0 is included, but 10 is not included. Why is that? At what time before 10? So 10 is not included. In essence, this is half closed, half open. 0 is included, 10 is not. Because 0 is included, we have already evaluated. If we want to go with the closed interval theorem, we need to have a closed interval. This is not, therefore we can't. However, the endpoint 0, which is included, must be calculated. It is. Now we go with the critical point. So let's differentiate, set it equal to 0. We get negative 6t squared plus 24. If we take out the negative 6, because we want to set it equal to 0 class. We get t squared minus 4, which is t plus 2, t minus 2 in any order. And there are two answers. This gives you negative 2, this gives you positive 2. Because t refers to time, we only accept the positive 2. So one more time. There are two answers, class. T equals negative 2, t equals positive 2, for many reasons. One reason t is time, the other one, if you look at the interval, 2 is in the interval and negative 2 is not. If we go with the first derivative test, which is a very simple case, take a look. This is 2, t is 2, and n prime is 0. We really don't go from negative to positive infinity. In essence, we go from 0 to 10 as it's given. But for the sake of evaluation for the test point, to the left of 2, you can even plug in 0, okay? And when you plug in 0 into either this one or the factored format, makes no difference, you get a positive. And then just they alternate, so positive, negative. That means this positive means increasing here, negative means decreasing here, increasing, decreasing, okay? This is the location of a maximum. So maximum occurs at t equals 2. What I want to mention here is really the importance of the second derivative test. You're done. You don't have to do the second derivative test. But because it's application, now it really makes sense to discuss the second derivative test. How does it work? Number one, you take n double prime, okay, which is obviously negative 12t. And then you have to plug in. It's either concave up or concave down. Notice what happens. N double prime is negative 12t. If I plug in my critical point of t equals 2, gives me negative. Negative means what? Concave down. How does it look like? Like so. Therefore, the maximum occurs at this point. So how does so you don't have to do this. Instead, you do that. How? Find n double prime of t and plug in 2. Negative means concave down max. Positive means concave up mean. It's that simple. Now, what is the maximum population? Plug in 2 into the original function. I hope you realize this is 4. 5 minus 4 is 1, okay? Just in case. And when you do the math, you get 132. This is 4. This is 1. So this is 28. So 28 plus 2 times 2 times 1 is 32 with 100, 132 million of bacteria. 132 million of bacteria. Okay, we want to graph this one. And again, what I like to do is to look at the graph using precalculus. So let's go over that, everybody. We want to go over this function using precalculus. So let's see if we can try to graph this. It may not be to scale. So I'm going to start with y sub 1 equals. And before I do that, let me rewrite this for you so you see what you're dealing with. You're dealing with the cube root of x minus 2 squared plus 1. So y sub 1 is the cube root of x to begin with. Again, this is not to scale by any means. Number 2, cube root of x minus 2 shifts to the right by 2. Again, not to scale, class. Okay. Number 3, cube root of x minus 2, we are going to square. If you recall from algebra, when we square it, there are two parts. The positive part gets larger, and the negative part flips over and gets larger. Okay. Number 4. Now I have f of x, which is the cube root of x minus 2 squared. I'm going to add 1. That means I'm going to shift it up. Let's assume this is not to scale again. Let's assume this is 1 here. So I'm going to shift it up by 1, and the graph looks like that. So what we did, we used precalculus to come up with the answer. And by the way, you notice there is no x-intercept, and there is a y-intercept here that all you have to do, plug in x equals 0. If I do that, I get cube root of minus 2 squared plus 1, which is cube root of 4 plus 1. So the y-intercept has the precise location. If I were to give it a location, would be 0, cube root of 4 plus 1. And I would use calculator to roughly estimate that, okay? So let's do that and see what happens with more information coming from calculus. So we are going to differentiate this, which means 2/3 x minus 2 to the power of 2/3 minus 1, or negative 1/3, times the derivative of the inside by the chain rule, which is 1. And we can rewrite this by taking this down, making it positive 1/3 or the cube root. Now, f prime is 0. F prime doesn't exist. A fractional expression is 0 when the top is 0. Since the top is a number, it can never be. A fractional expression is undefined or doesn't exist when the bottom is 0. So when you set this one equal to 0, you get x equals 2. I want to make sure we understand how we arrive at that. For this part, we said this is equal to 0. In other words, 3 times the cube root of x minus 2 is 0. And that results in x equals 2. Let's do the sine graph on that. Here's how the sine graph works. 2 is the only critical point. At x equals 2, f prime doesn't exist. What happens to the left of 2? Pick a number. What is the easiest number? 0. TP, short for test point 0. And if you plug in 0 into this, what happens? This becomes negative. Cube root of negative is negative. The whole denominator is negative, so positive over negative is negative. And if you pick a number to the right of 2, 5, 4, 3, anything, it makes the denominator positive and the numerator is a positive number. What does it mean? It means it's decreasing here and it's increasing here. Decreasing, increasing. Okay. So what does it mean? Minimum occurs at x equals 2. And I hope you realize that you have to find a pair. What do you do with number 2? You put it back into the original function. And this is a very easy calculation. When you put it in, this becomes 0 and goes away. The answer is 1. So you are going to write local mean is equal to 1 at 2, 1. There is no local max. Decreasing from negative infinity to 2, increasing from 2 to infinity. Okay, let's differentiate it again. We are looking at the inflection point, right? F double prime, 2/3 times negative 1/3 makes it negative 2 over 9, x minus 2 to the power of minus 1/3 minus 1, which is minus 4/3. Okay, minus 4/3. And you can take it down and make it positive, by the way, right? Positive 4/3, you can write it in this fashion. We can do the sine graph. We're going to discuss that just in case. But I hope you realize that this expression, when x is 2 is undefined. But other than 2, the denominator is always positive. Why is that? Because this is exponent even, 4. And a negative number over a positive is always negative. So this is always negative with the exception of 2. With the exception of 2. And negative means concave down. However, you can't say it's concave down from negative to positive infinity because at x equals 2, it's undefined. But let's go through the process. If f double prime is 0, it doesn't happen because the numerator is a number. If f prime doesn't exist, the denominator is 0. If you set this equal to 0, it gives you x equals 2. You do the sine graph on that. And by the way, I've already said that it's less than 0, always with the exception of x being 2, because what happens at 2, the denominator becomes 0. Here's the sine graph. Why is this negative? Why is this negative? If you, again, I've discussed that here, this is always negative. If you want to go with the test point to the left of 2, pick a easy point of 0. Okay. Let's say, I want to put it here because I need this space. So pick up TP of 0 and plug it into this function. 0 makes this positive, remember. Why is that? Because of this exponent. This becomes negative. Cube root is negative. To the power of 4 is positive. The whole thing is positive. Negative 2 over positive makes it negative. That's how we arrive at it. Do the same thing. To the right of 2, like 4, 5, 3, any number makes it positive. So negative over positive is negative. Therefore, we are going to say it's concave down, but we're not going to say it's concave down from negative to positive infinity. It makes no sense. Negative infinity to 2, union 2 to infinity. We want to find the intercepts. I have already discussed the intercept as far as the y-intercept is concerned. Also, there is no x-intercept. You saw the graph. I want to show you algebraically why there is no x-intercept. X-intercept, you set y equal to 0. So we're going to set this one equal to 0. If I set this one equal to 0, that means this. Okay, I'm going to raise both sides to the power of 3. And I hope you remember from algebra, this has no solutions because x minus 2 squared equals -1. No real solutions. And you need real solutions for intercepts. Let's go over the points that we have. Here's the summary. Y-intercept is at 0, cube root of 4 plus 1. For the sake of graph, it's about 2 point, let's say 6. Roughly. Extra point 1, 2. Why is this easy? If you plug in one class, you get -1. -1, cube root of that is -1. Square it becomes +1 and 1 and 2. So that's an easy point. 2, 1. I hope you remember that we had this minimum. Extra points. Again, I want to go with easy point. If I plug in 3 here, I get 1. 1 to the power of 2, there's 1 and 1 is 2. So 3, 2 is easy. This is not easy. I just did that just to make a point. You can use a calculator. If you plug in -1 on the left side, -1 minus 2 is -3 to the power of 2/3. You need a calculator and it becomes 3.08. Okay, roughly. But again, I picked up a couple of easy points. If I plug in -6 with -2 gives me -8. What is, remember, 2/3. That what is cube root of -8? -2 to the power of 2 is 4 plus 1 is 5. If I plug in 10, 10 minus 2 is 8, cube root of 8 is 2, 2 squared is 4, 4 and 1 is 5. Again, easy point. Put them all together. This is your local mean, okay? This happened to be an absolute mean also. There are more discussions here I want to show you, and this is the discussion. This is a relative minimum, also an absolute mean, okay? Decreasing here, increasing here, concave down, okay? There is no change in concavity. Both of them are concave down. That's why this is not a point of inflection.